Hi,
Hi, Professor Naresh. How are you?
not too bad, thanks.
All right. It's already 8.
Yeah, it's 8
Yeah.
o'clock already in Sydney.
Yeah. Apologize to interrupt your break.
No worries, no worries. Today is also Deepavali. It's like a Indian festival.
It's already 8.
Yeah.
Is it today, the
Yes.
Deepavali?
Yeah, it is
Ah,
today. Yes.
Congratulations then.
Oh, thank you.
And how was the celebration in there?
In Sydney, it's a bit quieter this year because of COVID, but still, I think people are sending greetings to each other and buying sweets. The sweets shop had a big queue.
Yeah, that's nice thing.
Yeah.
Yeah, I
And-
thought it's holiday.
Yeah, holiday in India, I think, but not in Australia.
Yeah, because in Malaysia, I think it's holiday also.
Yes, that's
Yeah,
right.
for
Malaysia
November,
and
yeah.
Singapore, they have a holiday as well. Yeah. Yeah, we are quite open now already, actually. Sydney, a lot of the restrictions are gone now.
Okay.
So
But
we are
then,
back.
yes, please.
Yes, sorry, we are back to opening everything now.
Okay.
Yeah.
But the number of the COVID is like declining already.
Yeah, it's declined quite a lot actually because our vaccination rate is now very high. Like in New South Wales, I think we're nearly reaching 90% vaccination now.
Okay, nice.
So that's why the government is opening up.
Yeah.
Yeah, I think it's also open for international students.
Yes. So we can actually now travel to Singapore, travel to UK and US as well.
Yeah. Yeah. So some of my friends who actually postgraduate students at UNSW are complaining because they can't go to Sydney.
Yes. I think after December, it will be possible, I think, for students. Yeah.
Oh, yeah.
Because I have one student in India and 2 in China. They are stuck. Hopefully they can come back soon.
Yeah.
Bu video, what time should we start?
10 minutes.
Okay.
Yeah, 4:20.
Okay, 4:20. Okay.
Yeah.
I was just going to check my slides that they are uploading. All right. I just tried a video and then just see that they're okay.
Yeah.
You might have to enable the sharing, I think.
Okay. Sorry. Yeah, you can try.
Yes.
All right.
Okay. Can you see my screen?
Yes.
Good. I just wanted to see if I just go full screen, can I use my pen to write on the slides? I think I can't do that if I have it in a full. I just check that. No, if I go full, then I can probably have pen. Okay.
Yes.
So it's a pointer, pen. Okay. Because I want to try to write something if I can. Yeah, that'll be good. Yeah. Because it's sometimes a little bit easier to explain things when you can write.
Yeah.
Yes. Especially for chemistry and in organic chemistry, you have to
Yeah,
draw
that's
everything.
right. That's right. Yeah. There's nothing like writing on the board. I think that's always the. All right, I'll stop sharing now and then I'll start later.
The video, I thought it start at 4. It's 4:20. Okay.
Yeah, 4:20.
That's why I'm too early. I was asking Bu Video why I cannot enter the Zoom, and then she said that it even not open yet.
Yeah.
How is the season now in Sydney?
Sydney is open now fully. The traffic is back to normal, and we can have face-to-face meetings, and people can go to restaurants and sports gymnasium. Sports stadium, you can have full capacity. Yeah. So it's only came in a few days ago that we have lifted a lot of restrictions. Cinemas are also open. So there's some normality coming, I think, and hopefully by Christmas, everything will be back to normal. But I think people are very keen to travel at the moment, but
yes, after 2 years.
Yes,
yes.
That's right. That's right. Yeah, I haven't traveled for the last 2.5 years now.
Yes, I think almost all of us, yeah.
Yeah.
Even I think for the last, I don't know, because in Indonesia we have like a peak of the COVID in May, June, or July, yeah. So I think even I never go far from like 2 kilometers. So I just like circle inside the resident, and it's like,
yeah, that's true.
yeah, it's like crazy.
Yeah, when we had restrictions, we couldn't go beyond 5 kilometers from
Yeah.
our house.
Yeah.
And the funny thing was, there's a big shopping center near my house, which is only about 400 meters away.
Mm-hmm.
But then that part was cut off because that was a zone where we couldn't go. So we couldn't enter that road.
Even only 400 meters, yeah?
Yeah, that's right. That's right. So
yeah.
Yeah. All right, I'll join back in a couple of minutes.
Okay. Saya pikir Bu Vidya jam 4. Nah, kayak
Tadi Ibu sudah datang.
Kenapa ya nggak bisa join ya, kata saya.
Jam 4.20 agak nanggung gitu ya, Bu.
Yeah.
Ini kan untuk yang kelasnya Ibu bukan ya, Be? Sama Prof Asep?
Karena saya berpikir jam 4, saya nggak masuk lah ke kelasnya Pak Asep. Karena saya pikir langsung ke sini gitu loh. Terus lah, baru sedikit yang hadir.
Iya, tadi kata Bu Amel katanya, iya masuk dulu jam 4. Baru habis itu ke sini.
Saya agak very occupied Bu Vidya, karena saya ikut pelatihan auditor halal kan 2 minggu. 2 minggu duduk di depan Zoom gitu ya, belum udah ngerjain tugas. Nah, kemarin praktek dan ngumpulin tugas itu hari Minggu. Jadi saya selesai hari Minggu jam 1 tuh baru beres tuh. Taunya ujiannya hari Rabu. jadi hari
kemarin, Bu.
Iya, jadi hari Selasanya saya harus memanage course di SPS. Hari Rabunya saya ujian. Prof Asep, mohon maaf, tadi saya nggak masuk kelas loh, saya nggak tahu. Kirain masuk langsung ke sini.
Enggak, kita ngobrol dulu sedikit ya. Oke, para mahasiswa, saya mohon Anda nyalakan videonya ya.
Assalamualaikum, Prof Asep.
Waalaikumsalam, Bu Vidya. Saya itu udah minta mereka untuk bikin pertanyaan melalui chat ya. Tolong coba dibaca.
Oh iya. Iya. Nanti juga akan iya, Pak.
Oke ya. Jadi terima kasih nih yang sudah menyalakan video. Kalau Anda yang belum menyalakan video, coba berusaha. Kecuali memang kalau koneksinya betul-betul tidak bagus ya. Kalau betul-betul koneksinya tidak bagus.
Ini ada fotonya Vanessa-nya terpental.
Gak apa-apa ya. Silakan, nanti video akan bantu.
Nanti akan ada latihan.
Itu sopirnya.
Oke, bagus.
Tapi terpental.
Bu Vidya sama Bu Sitaisa mungkin nanti anak-anak dibantu ya kalau ada pertanyaan, biar maksud saya bisa, kan ini pengalaman bagus juga. Jadi pengalaman bagus bagi para mahasiswa untuk bisa berkomunikasi gitu ya, dengan dosen lain ya, karena kan itu bisa membuka wawasan kita. Saya udah tugasin juga mereka untuk nyalakan. Jadi dari kelas saya sekitar Kalau saya dengan Bu Ais, Bu Amel itu sekitar 80 Bu yang akan gabung. Ini baru berapa nih? Baru 74. Anda boleh bertanya ke sama Bu Vidya. Bu Vidya lulusan dari New South Wales. Bu Vidya dari mana?
Iya, betul Bapak. Dengan Prof. Naresh.
Oke, Prof. Naresh sudah hadir. Oke.
Hi.
Halo, Prof. Naresh. Good afternoon.
Hi, how are you?
Fine, good.
Good.
Okay, thank you for your time to give
No
lecture
problem. No
for
problem.
us.
No problem. It's a pleasure.
Okay.
There is a 4 hours difference between Sydney and Bandung. I think it's nearly 18 past 8 here in Sydney.
Oh, I see. In 18, Bandung is now is 16:20.
Yeah, it's 4 hours difference because our clocks went forward 1 hour a couple of weeks ago.
Yeah.
So we have daylight saving because we are going into summer.
Okay.
Yeah.
How was summer in Sydney? Is it hot?
Yeah, it can get quite hot. Sometimes, especially west of Sydney, it can go up to 40 degrees, 42 degrees.
Oh my God.
Yeah.
It's quite hot.
Yeah.
Bandung now is good weather. Yeah.
Yeah.
Cool.
That's
Bandung
good.
is cool now.
All right.
It's not good, Prof. Asep, because it's raining. It's raining every day. Yeah.
But I like with the rainy, why? Because I can sleep well, yeah.
Yeah. Rainy weather is good for sleeping, I think.
It's flood, everyone.
All right. Okay.
Bu Vidya, shall we start? Or should we wait?
Yeah, I think it's already 4:20. I think we can start now.
Okay.
Yeah,
Yes.
please.
Terima kasih Bu Vidya. Prof. Naresh, I will speak in Bahasa first.
Okay, no
Okay.
problem.
Bu Vidya, can you mute? I think someone is still unmute.
Oh yeah, please wait.
Thank you. Ya, adik-adik mahasiswa, Prof. Asep, Bu Vidya, saya coba ada lagi dosen yang lain nggak Bu Vidya? Bu Gebi atau Bu Ratna?
Bu Amel.
Ada Bu Amel, ada Bu Gebi juga. Ada Bu Gebi, selamat sore Bu Gebi. Ada Bu Amel, kemudian ada Bu Ratna kah? Pak Iqbal? Oke, ya. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Adik-adik mahasiswa, Ibu dan Bapak dosen, pada saat ini kita akan mengikuti kuliah umum dari Prof. Naresh Kumar. Bu Vidya, still some noise. Kita akan mendengarkan kuliah dengan topik struktur dan reaktiviti dari senyawa polifungsi, yaitu reaksi pada senyawa dikarbonil. Jadi ini memang topik yang cocok ya, Prof. Asep, dengan topik mahasiswa yang sedang mengambil kuliah kimia organik 2 yang tentang polifungsi. Oke, kita mulai ya. So, good afternoon, Professor Naresh Kumar. Welcome to the program of Visiting Professor Lecture Series on Organic Chemistry with Prof. Naresh Kumar from UNSW, Sydney, Australia. My name is Siti Aisyah, and it's my pleasure to be the moderator for this session with the title Structure and Reactivity of Polyfunctional Compounds, Reaction of Dicarbonyl Compounds. Since I think in the previous session, Bu Vidya already introduced you to others, so I think in this session, without further ado, I would like to welcome Prof. Naresh to deliver the topic. Prof. Naresh, the time is yours.
Thank you very much. Thank you for the kind introduction. And I'm going to start sharing my screen so that you can see my slides. Share. Okay. And I'm going to get a pointer so that I can scribble some things on the slides as we go along. Okay. Very good afternoon, I think, for you, and it's actually a nighttime for me. As I mentioned, we are 4 hours ahead of you in Sydney, and it's nighttime here. What we're going to do today is going to talk about chemistry of dicarbonyl compounds. And I'm going to talk about, first of all, a little bit of introduction on carbonyl compounds, which you might have studied in your first year. And then from there, move on to the chemistry, which is happening adjacent to the carbonyl group, as well as compounds which have more than one carbonyl group. And let's see what happens there when that's the situation. If I just go to the next slide. Okay, just a quick revision. So what are carbonyl compounds? I'm sure all of you know what carbonyl compounds are, and these are basically, compounds which have a carbonyl group, and the carbonyl group is typically represented by a C double bond O. This group is called as a carbonyl group. And this group is present in aldehydes, present in ketones, as well as carboxylic acids, because you can see even a carboxylic acid, you have that group present in it. And you, as you will know from your first year, that in case of aldehydes, there is at least one hydrogen attached to the carbonyl group, while in the case of ketones, you have 2 carbon substituents attached onto the carbonyl group. And while in the case of carboxylic acids and their derivatives, the carbonyl group always have an oxygen substituent attached adjacent to the carbonyl group. So this becomes like a COH, but if there's other derivatives of carboxylic acids like esters, then you have a O carbon group attached onto the carbonyl group, which is present in these molecules. And the carbonyl compounds are quite interesting compounds. And a lot of chemistry can be done with the carbonyl compounds. And carbonyl compounds are not only important in nature, but they are also very important from industry perspective as well, because you have a lot of applications where carbonyl compounds are used. For example, just to give you some examples of aldehyde compounds, for example, vanillin. Vanillin is a molecule which comes from vanilla beans. And you would have all tasted vanilla one way or the other. If you go to McDonald's and have a vanilla milkshake, that has vanillin in it. And vanillin is also used in a lot of cooking and cakes and the like. And benzaldehyde compound, a simple benzene containing aldehyde compounds, comes from almonds. And this has that peculiar almond flavor you get when you eat almonds is because of this chemical. And similarly, cinnamaldehyde comes from cinnamon, and cinnamon is again a spice that is used in a lot of cooking as well as cakes as well. And there is the aldehyde group present in that compound as well. And the small molecule, like simplest possible aldehyde, is formaldehyde. And formaldehyde is the chemical that is used for preserving tissues. So if you go to a biology lab and you see a specimen stored, a biological specimen stored in some liquid, the chances are it contains that formaldehyde group. And acetaldehyde, the next molecule after formaldehyde, is the chemical that is responsible for the hangover feeling people get when they drink alcohol. Next day they feel groggy, and that is because of this chemical that is produced from alcohol when it is metabolized in the body. Similarly, the ketones are also quite important naturally as well as industrially. If you look at this ketone molecule here, it's called methyl isobutyl ketone. And this is a commonly used solvent in paintings, in coatings, very common industrially used chemical. And another example of it here is a raspberry ketone. And this is again a ketone compound. And raspberry ketone is used, it comes from red raspberries, which we eat. And it is used in perfumery, cosmetics, and as a food additive as well. So again, highlighting that the carbonyl compounds are very, very important. And also acetone, those of you who have done some work in the lab, you will see that acetone is used in the lab quite commonly to clean up glassware and also a very commonly used solvent in industry as well. And this is another example. The carbone is a natural oil with the spearmint odor. So like when you get the spearmint mint smell is because of this carbone chemical, which again has a carbonyl compound in it. Okay, so what I'm trying to highlight here is that the carbonyl compounds are very, very important. And you would have read about aldehydes and ketones and carboxylic acids in your first year. And you might have also, when you learned about carbonyl compounds, heard about or learned about this term called Keto-Enol Tautomerism. So what do we mean by Keto-Enol Tautomerism? Because that got quite a lot to do with the lecture which we're going to do today. And we're going to be looking at quite a bit of enol chemistry. What we have seen so far is that the carbonyl compounds existing as C double bond O. But there is another possibility in the carbonyl compounds when particularly you have a CH group present adjacent to the carbonyl group. So in majority of the cases, you will find that the carbonyl compounds, the ketone compounds, they exist in the carbonyl form, like a keto form, C double bond O. But when there is a CH present next to the carbonyl group, there is a possibility that you can form what we call an enol. By enol, we mean en stands for a double bond. In organic chemistry, if a molecule has an en present in it, and that en typically means a double bond. And if you have an enol, that means there's a double bond and an alcohol present as well, because OL, all in a molecule, stands for an alcohol. So that means this molecule has a double bond as well as an alcohol. That's why it's called as an enol. But if you take a normal common ketone compound like acetone and cyclohexanone, and then look at their structure by, say, nuclear magnetic resonance spectroscopy, you will find that the majority of these compounds, they exist as the keto form. Greater than 99.9% exists in the keto form acetone compound, if you have the acetone compound. And if you look at cyclohexanone, 98.8 exists in the keto form, and there is 1.2% in the enol form. And in the case of acetone, less than 0.1% exists in the enol form. So the question you might ask is that why does it exist in the enol form? Why there is enol form possible in these cases? And is there a driving force? Is there some sort of stability which is happening when a ketone is going to the enol form? And we'll look at the details of that in a minute. And one thing to remember is that keto-enol, they are what we call tautomers. They are not resonance structures. They are isomers in equilibrium, right? But this keto-enol tautomerism can shift towards the enol side if there is some stabilizing factor is present in your compound. And that's very relevant to today's lecture, because today's lecture, we're going to talk about dicarbonyl compound, that means which have two carbonyl groups present in a molecule. And also we're going to talk about chemistry that is possible adjacent to the carbonyl group. So if you take the example of a ketone, a dicarbonyl compound, which is like a 1, 2, 3, 4, 5, 2, 4, 1, 2, 3, 4, 2, 4 diketone compound, you will find that the enol form in this case is present in 76%, while the keto form is present only in 24%. So the equilibrium in this case lies towards the right-hand side. And the reason for this equilibrium lying towards the right-hand side in the enol form is that there is a hydrogen bonding possibility possible in this molecule here. That means one of the carbonyl groups here can form a hydrogen bond with the OH group that is present on the enol. Okay, and that hydrogen bonding possibility shifts the equilibrium to the right-hand side, and the enol tautomer is stabilized by the intramolecular hydrogen bonding that is present in this case. So that means the carbonyl compounds don't have to exist as C double bond O all the time. They can also form what we call enols. And if they can form enols, then there's a new chemistry possible adjacent to the carbonyl group. Because at the moment, all the chemistry you have learned about the carbonyl compound is that the carbonyl bond is a polar bond. You have all learned in first year that the carbonyl bond here is a polar bond. The reason why it is polar bond is that oxygen is more electronegative. So that means the pair of electrons is more shifted towards oxygen. That's why the oxygen has a slight negative charge. And the carbonyl carbon, on the other hand, has a slight positive charge. And because of that polarity that is present in a carbonyl bond, you would have learned that all the reactions of carbonyl groups happen at that carbon over there. So if you got a nucleophile, and this nucleophile can be a Grignard reagent, and the Grignard reagent, as you know, is represented by, say, R, Mg, X, where X can be a chloride or a bromide. And the Grignard reagent will attack this nucleophiles, carbonyl at the carbonyl carbon. And this doesn't have to be a Grignard reagent. It can simply be a hydride reagent like H-. It can also be an amine that can react with say if you have a R NH2 like an amine, that will also react with the carbonyl group in a same manner, where the nucleophile, in this case nitrogen, the lone pair of electrons, will attack the carbonyl carbon, giving you the addition product. So the nucleophiles will add across onto the carbonyl double bond to give you an addition of a nucleophile to the carbonyl groups. That's the standard reaction of the carbonyl compounds, which you would have studied in your first year. But because the carbonyl compounds can form also enols now, is there a different kind of reactivity possible with this carbonyl compounds? And that's what we're going to be learning today in the lecture today and the next week as well. Okay, so let's see. How is it possible to form an enol? Why the CH group that is present adjacent to a carbonyl group behaves in a way that it can form an enol? The reason is that if you remove this proton that is present on the carbon adjacent to the carbonyl group, so I bring in a base, for example, and the base can take away that proton that is present on the carbon here, you're going to get an intermediate situation where you're going to get a carbon with a negative charge. Okay, so we remove that proton with the base and we get a negative charge here. And the negative charge here can be stabilized, or the anion, carbon with a negative charge is called an anion. This anion can be stabilized by resonance. So the pair of electrons come across here, and this pair of electrons shifts onto the oxygen. And the result of that is going to be, which is on the next slide, but I can draw it for you here as well, is that you're going to generate and O minus over here, right? Because we shifted the pair of electrons over here, you got your substituent still present on that carbon. So this is what is going to happen if you remove that proton, which is adjacent to that carbonyl group. And this is a bit like an acid-base reaction, right? Like if you have an acid, for example, HA, if I represent HA as an acid, and by definition, an acid is a compound which can give away a proton, right? So by definition, we can say acid is a compound which can give away a proton, and you have plus A minus, which is the counter ion or the base that is present in an acid, right? So this is what happens when you have an acid. Acid dissociates and it gives a proton, right? The same thing is happening here. If you look at that CH here, the CH is giving away a proton to this base to form this carbon ion. So that means this CH is acting as an acid when it is present adjacent to the carbonyl group. And we call that CH as a carbon acid. So carbon acid is a compound which is relatively acidic, hydrogen bonded to an sp3 hybridized carbon. So that means this carbon is sp3 hybridized carbon, and this proton can be removed. So that means the CH that is present adjacent to a carbonyl group can act as an acid. That means can be removed by a base. And that anion that is formed is stabilized by resonance because there's a carbonyl group present adjacent to it. So just rewriting what we learned in the last slide, there is your acid, the CH, present next to a carbonyl group. A base comes around, can take away that proton, and if it takes away that proton, you generate this carbon ion here with a negative charge. And this carbon ion here is stabilized by resonance to form this structure here. And then this O minus can take a proton back to give this structure called enol structure. And as I explained to you earlier, an enol is a compound which has a double bond as well as an alcohol present in it. So there is this Keto-Enol Tautomerism that is possible in the carbonyl compounds, particularly the ketone compounds, to give the enol form because of the stabilization which is there because of the resonance. So one thing you might ask is that we have a C minus here and an O minus here. So there are two possibilities. A proton can add either to the oxygen or it can add to the carbon. If the proton adds to the carbon, you basically go back. It's like a reversible reaction here, right? The arrows indicate that this is reversible. But if the hydrogen adds to the oxygen, then it becomes an enol form, and the enol form is the resonance structure of the carbonyl compound. And oxygen is able to better accommodate the negative charge because oxygen is more electronegative compared to other atoms, for example. Okay, so what I've done is shown you that you can get this keto-enol tautomerism or enol form of a ketone, which can show a different reactivity to the reactivity we have seen with the carbonyl group so far. So is this a general phenomenon? Is this phenomenon present in all compounds which have a carbonyl group? And which carbonyl shows the highest electron withdrawing effect so that the CH is more acidic? So what is there in this table is that this table has lots of compounds here. And you can see there is different kinds of carbonyl compounds present here. And some of them are amides. For example, this is an amide here. This is an ester here. This is a nitrile here. This is a ketone here. This is an aldehyde here. And then this is a diester compound. a dinitrile compound, a keto and an ester, and 2 ketones, and then you got 2 ketones here as well. Then you even got a nitro, because nitro is also a very strongly electron withdrawing group. You got a ketone and aldehyde, and you got 2 nitro compounds. And adjacent to that, you have this number called pKa. The pKa value actually tells you how acidic the CH is adjacent to that carbonyl group. So if you look at this CH that is highlighted in yellow in all these structures, that's the CH we are talking about. That's the proton that can be removed to generate that carbon ion. And that's the proton which is acting like an acid group in those molecules. And the numbers here represent how acidic that proton is. If this number is a small number, that means this compound is more acidic. And if this compound is a small number, is a large number, that means this compound is less acidic compound. And straight away, you can see that we're going to be dealing mainly with carbonyl compounds. You can see that the carbonyl compound, where there are 2 carbonyl groups present, like this example here, got 2 carbonyl groups. This has 2 carbonyl groups. This has 2 carbonyl groups. This has 2 carbonyl groups. And this has 2 carbonyl groups. They have a lower number. That means they are more acidic. This CH is more acidic compared to when you have only 1 carbonyl group present. For example, in case of amide, this number is 30. So that means this proton is less acidic. And if you have a ketone or an aldehyde, then this proton is more acidic. So that means it'll be easier to remove that proton with a weaker base if it's a strongly acidic proton. And we'll see the implication of that as we go along. Now, if you compare an ester with an acid, with a ketone, so ketone is CH3, C double bond CH3, that's acetone, ketone. And this compound is an ester because it got a CO oxygen and a carbon substituent. And if you look at the acidity difference between these 2 protons, you can see that the pKa of acetone is 20, ester is 25. So that means this CH here is more acidic in acetone compared to this CH here in ester. What is the reason why acetone is more acidic than ester? The reason is there is an alternative resonance structure possible in the case of esters. But let's look at first the normal delocalization we get if we remove this proton, as we saw in the last slide. So we are looking at the red arrows now. If you remove this proton, move this pair of electrons, you'll get the normal enol, which we saw in our last slide. So that was like the normal enol that was present. But there's an alternative resonance structure possible, which is shown by the blue arrows here. The pair of electrons on the oxygen that is present on the carbon can also participate in a resonance structure by delocalizing this pair of electrons. And if that happens, that's going to interfere with the normal resonance that is possible in the case of in the case of ketones. So that means the electrons that are present in case of esters are not readily delocalized because of the electron release by this oxygen functionality, the blue arrows which I indicated. So that means when you're comparing the reactivity of the aldehydes and ketones with esters, the aldehyde and ketones are going to be more reactive. And the same thing applies to when you have diketones present. This is like a 1,3-dicarbonyl compounds. This is a diketone compound, while this one is a keto group and this one is an ester group. So there's a keto-ester compound here. And you can again see the acidity difference between the diketone compound and the keto-ester compound. The diketone compound is more acidic compared to the keto-ester compound. And the reason again is that if you have 2 carbonyl compounds, 2 ketone compounds present in one molecule, there are more resonance structures possible. you can say this is our starting compound here. You can remove this middle proton. This is the acidic proton. And when you remove this proton here to generate this carbon ion, this can be stabilized by resonance on the right-hand side. And this can also be stabilized by resonance on the left-hand side as well. So you can see that you can get resonance stabilization by this way, and you can also get resonance stabilization by this way. So if there's a double resonance stabilization of the carbon ion, that is going to be more acidic compound compared to, say, for example, with one ketone compound or a compound with one ketone and one diester, because the oxygen lone pair here, which is present on this oxygen, is going to interfere with normal resonance stabilization. That's why this is more acidic compared to the ketoester compound. Okay, so the question is, this interconversion we talked about, going from the keto compound to the enol compound, can it happen in the presence of acid? What we saw so far is that we had a base, and the base removed the proton from the acid, and we got the anion, and the anion got resonance stabilized. So the question is, can this happen in the presence of acid? Can it be acid catalyzed? The answer is yes. How can it be acid catalyzed? So you can imagine you got a carbonyl group and you got an acid. So acid is represented by, you can write acid as H plus, or if there is water present, you can have acid as H3O plus. That's the standard way you can write these acid. So I have written this here as a HO3 plus, sorry, OH3 plus, oxygen OH3 plus. And the carbonyl here can be protonated by acid to form an OH plus species. So you can imagine if you protonate this oxygen here, you will get this OH plus species. And if that species is formed, then water is able to remove that proton that is present on the carbon adjacent to the carbonyl group. And you get similar stabilization again to give you the enol form, which we saw earlier. So that means the enol form can also be generated by using an acid catalyst rather than using a base. So it can be catalyzed both by acid as well as base. So in the case of acid, you get protonation of the carbonyl first, and then you get a removal of the CH to get the enol form. While in the base conditions, you directly remove that proton from the CH2 to get the enolate form, which then get protonated. So that means this reaction is possible both in acidic conditions as well as under basic conditions. So what happens in base-catalyzed keto-enol conversion? As I mentioned earlier, the base can remove that proton that is present adjacent to the carbonyl group, because this is an acid, this is a base, so base takes away that proton, and the carbon ion that is generated is stabilized by resonance to give us this species called enolate. So when you have a minus on the oxygen, this is called as enolate, E-N-O-L-A-T-E, this is called as enolate. Excuse the writing because this pen is hard to use, enolate. And once it gets protonated, then it becomes the enol form. So that means you can convert a ketone to an enol form either using acid or using base. So that means you can do the reactions with these ketone compounds by using either acid or base. And we'll see the implications of that in a minute. Now, how do we know what guarantee we have that there is a Keto-Enol Tautomerism taking place? What is the guarantee? What is the evidence that this is an acidic proton? What is the evidence? All we are saying so far is that the base comes and removes this proton and forms enolate and then becomes enol. But all these conversions so far have been reversible. If you look at this reaction here, this reaction scheme here, or the scheme represented here, all these arrows you can see, they are all, this is resonance structure, they're all reversible. So what is the evidence? How can we say 100% that there is an enol formation happening? And the evidence comes if you take a carbonyl compound like that and treat it with the deuterated acid or deuterated base. So D here stands for deuterium. And if you take a ketone molecule, dissolve it in deuterated acid, like deuterated acetic acid or sodium deuteride, you find that the product that is formed by just dissolving this compound in deuterated acid or a base has got these hydrogens replaced by this deuterium. And the way it happens is exactly the same way we seen before. In base or acid, you're gonna generate the C double bond O minus, like say we are talking about base here, and you're gonna have your double bond, and you're gonna have your hydrogen, and you're gonna have your R group here, right? And when there is deuterium present, the deuterium can come and form OD here, and then the OD can go back to the keto form to leave the deuterium on the carbon that is present over there. So this gives us the evidence and that there is deuterium present in our molecule. And if there's deuterium present in our molecule, that is telling us that it is going via this enol to form this deuterated compound. And the deuterium compounds can be characterized quite easily by NMR spectroscopy. So if you take this compound in a solution of deuterated acetic acid or sodium deuteride and put the NMR tube in an NMR instrument, you will find that there's deuterium present in your molecule. So that gives the evidence that we have got deuterium there. So what is the implication of this enol? What is so special about this enol? The special thing about this enol is that if you compare an enol with a double bond, so alkenes, as you know, you would have read about alkenes in your first year. Alkenes are compounds which have double bonds. Say, for example, if you take an example of a simple alkene compound where that is R group here and is a hydrogen here, and there is a R group here, and there is a hydrogen here. This is an example of an alkene, right? I'm just randomly drawing one alkene. And you will know from your first year chemistry that alkenes react with a lot of reagents to add across to the double bond. So you can do bromination, you can add water, you can do all sorts of reactions with the double bond. And you can also now see that this enol here also has a double bond. It's got a carbon-carbon double bond. But on top of that, one of the carbon has an electron donating group like an OH group. And OH group is a group which contains electron-rich oxygen. So that means this compound here is going to be much more reactive than a normal alkene because this has an additional electron donating group present, which is contributing to this double bond. So that means a double bond of an enol is electron rich. And if a double bond of electron is rich, then it's going to undergo reactions very, very quickly with a lot of electrophiles. So if you draw that arrows going back and the carbon got an anion, so that is going to be very, very reactive to give us the products. The reactions are going to happen at that carbon over here, which is adjacent to the carbonyl group. So if I have an electrophile which loves electron and is deficient in electrons itself, it's going to be attacked by this negative charge that is present on the carbon here and going to lead to the formation of substituted products. And we call these substituted products as alpha substituted products. Alpha, as you know, comes from Greek alphabet. Like we got A, B, C, D. A is the first letter in the English alphabet. Alpha is the first letter in the Greek alphabet. So this position here that is adjacent to the carbonyl group is called as an alpha position. So that means we're going to see a lot of reactions happening at the alpha position when you got this keto-enol tautomerism happening, and you got forming these enols in these reactions. So let's see some reactions of this system then. Before I do that, I got a quick question for you guys. I got 4 pairs of compounds here. There's 1, there's 2, there's 3, there's 4. And the question I'm asking you is, which of the following 4 pairs are not, so that I'm going to underline here, are not, I'm asking which one of these are not related as keto-enol tautomers. So you need to think about which of these 4 pairs we have are not keto-enol tautomers. And I can tell you that 3 of them are keto-enol tautomers and 1 is not. And I want you to think about which of these 4 is not a keto-enol tautomer. And I'm going to give you 1 minute or 2 minutes to think about it before I tell you the answer. But think about it yourself and try to see which one of those is not related as keto-enol tautomer. Okay, you can check your answer now. You can see here that this compound, this group here is a CH3 group. So there's a hydrogen here. There is a hydrogen here and a hydrogen here as well. So there's just a CH3 group. So I just write it here. So that means you can remove one of these protons quite easily. If that proton comes off, you're going to get this structure. So this is related as keto-enol tautomer. Similarly, if you look at this structure here, this also have a hydrogen and a hydrogen and a hydrogen here. So I wouldn't spend too much time here, but I'll just tell you okay, it's a little bit harder to draw with this pen, but you can see that there's a hydrogen here as well. So that means this is also related as a keto-enol tautomer, because if you remove that proton, you get an enol. And the same thing applies here. You have a hydrogen here and a hydrogen over here. And this is also related as a keto-enol tautomer, because you remove that hydrogen, you get that enol. What about this structure here? If you have this structure has a hydrogen here and a hydrogen over here. And if you remove one of these protons, the enol you should get should be the one where the double bond is present at the top, not on the side. So the double bond should be present here, and the hydroxyl should go over there if it forms a keto-enol tautomer. So that means this is the one which is not a keto-enol, related as keto-enol tautomer, right? So this is the answer. This is the one which is not related as keto-enol tautomer. Okay, let's move on. So what can we do with this? So once we learned that there is this enol form possible in the presence of acid as well as base, and we also learned that it can cause alpha substitution of carbonyl compounds. So the overall reaction can be written as that if you have a keto form, and particularly we're going to look at now acid-catalyzed alpha substitution reaction. There's a base-catalyzed possible as well, but we're going to look at acid-catalyzed first as well. The top part, we have seen already that how in the presence of acid, you can form an enol. We have learned that already, the top bit. So in the bottom bit, I'm going to show you that if there's an electrophile represented by E+, comes in contact with an enol, this enol is going to attack that electrophile. And this can do that quite easily by moving that pair of electrons over here. And then that pair of electrons attack that electrophile, and the electrophile gets substituted at this particular carbon over there. And then this OH plus go back to the carbonyl by simply giving away that proton to give you an alpha substituted product. So let's now see a real example. This is just saying electrophile. Now let's look at this reaction in a real electrophile sense. And this reaction is responsible for what we call halogenation at alpha carbon. So remember the Greek alphabet. This position adjacent to the carbonyl compound is called as an alpha position. This is also an alpha position because that's next to the carbonyl. The first position next to the carbonyl is called as an alpha position. So that's what we are saying, that there's halogenation at the alpha carbon. So if you take cyclohexanone and treat it with chlorine gas or chlorine liquid in the presence of an acid H3O plus, you will find that it will give you the alpha substituted product. So that means the undergoing species in this reaction is Cl plus is your electrophile, and that gets substituted at the alpha position to the carbonyl. So you get a chloro over there. And similarly, if you have a compound like this, which got a carbonyl group, and it got a CH2, CH3, this position is called as your alpha position, and this position is called as a beta position, because in Greek alphabet, first position is alpha, first letter is alpha, and second is beta. But the reactions are only happening at the alpha position to the carbonyl, not at the beta position. So if you do a bromination reaction of this carbonyl compound, you will find that the bromination will give you the alpha substituted product. So the bromine gets added or substituted at the alpha position of the carbonyl to give you the corresponding bromo compound. And these reactions, the chlorination and bromination reactions, can typically be carried out in acetic acid. So the acetic acid acts as a solvent as well as a reagent, acid catalyst, to carry out the alpha substitution reaction. So one of the reactions which you can do with the enols is that you can do alpha substitution. You can put a substituent at the alpha carbon that is there in these carbonyl compounds. You can extend this reaction one step further. And that reaction can also be carried out with an acid group, alpha to the acid group, because acid also has a carbonyl group. So it also can be carried out alpha to the acid. And typically this reaction is carried out in the presence of phosphorus as a catalyst. And X2 is like a chlorine or a bromine, which you can use in these reactions. And the net result is that you put a substituent alpha to the carbonyl compound. You do alpha substitution reaction. It goes via this intermediate called acid halide when you have a COX or COCl in a molecule or COBr in a molecule. So if you have a COCl present in a molecule, these kinds of compounds are called as acid chlorides. You can have acid bromide. So it goes via this COCl in this case or COBr in this case, and then there's an alpha substitution happening to give us the bromo acid. So you just take a normal carboxylic acid. This can be any carbon length acid. It can be 6 carbon, it can be 10 carbon, it can be 12 carbons. You just treat it with bromine in the presence of phosphorus and work up the reaction in water. You will get the alpha bromo product forming in this reaction. And this reaction got a weird name. It's called Halogenation reaction, converting an acid to an alpha bromo acid. It's a very useful reaction because you can do a lot of things with this particular molecule that is generated. And it's a very simple reaction to do. Okay, so what we looked at so far is that we looked at the substitution reaction that happened in the presence of acid. The carbonyl compound formed an enol, and then the enol reacted with the electrophile. What about alpha substitution in the presence of a base? Can we do this substitution reaction under base-catalyzed conditions? The answer is yes. So under the base-catalyzed conditions, we learned so far that you can form this kind of enolate quite easily by removing the acidic proton that is present adjacent to that carbon, you can get that CH removed quite easily to form that carbon ion. And that carbon ion is then resonance stabilized to give us this enolate species. So the enolate species itself can also react with electrophiles. We saw in the last few cases, there was enol where we had the OH group here on the oxygen, but the enolate by itself, when you got a negative charge on the oxygen, can also do this electrophilic substitution reaction. So this pair comes here and the electron pair reacts at E+, forming that carbon E electrophile bond. Result is basically alpha substitution, because as we learned that this is the alpha position, so you get electrophile substituting at the alpha position. So what is the difference then? What is the advantage then doing the reaction in a base rather than an acid? The advantage, big advantage is then when you do this reaction in the presence of a base, or what we written here is the base promoted halogenation, that when you carry out this bromination reaction in the presence of hydroxide, so this could be sodium hydroxide or potassium hydroxide, is just a base, the reaction is much more faster. And the reaction is faster in the sense that you can replace both the hydrogens which are present here in this molecule to the corresponding bromo compound. Even if you got 3 hydrogens present here, all 3 can be converted into halogens. So obviously this reaction is going via the monobromination first. So you get the formation of the product which we got earlier in the presence of acid. You got the first thing that is going to happen is you're going to get a bromine here, for example, that is the monobromo compound, Br, hydrogen, and then you have your R group here present in it. So the first step is going to be the formation of the bromo compound. But because of the base that is present, this proton here can also be removed quite readily and can be substituted by the second bromine to give you the dibromo substituted compound. And under basic conditions, all the alpha hydrogens, it doesn't matter whether there's 1, 2, or 3, they can all be substituted by halogens. Say, for example, if you have a COCH3 compound, which has 3 hydrogens attached to it, and you do the reaction in the presence of excess bromine and base, you will get a compound with the 3 bromine atoms present on that carbon, and a CBr3 product is formed. While under acidic conditions, you will predominantly get the compound which just has 1 bromine, but when you do the reaction under basic conditions, you can replace all the hydrogen that are present in the molecule with the halogen chloro or bromo group in that structure. And there's an application of this reaction. And this reaction is called as a haloform reaction. And it is also forms the part of what we call an iodoform test. I don't know if you have carried out this test in the lab. It's a test for confirming the presence of a COCH3 group in a molecule. If somebody come to you and gave you a compound and tell you that this compound have got an ROCH3 group, can you confirm it for me by a chemical method that this compound has a COCH3 group? So what are you going to do? Are you going to start to think, oh, what I'm going to do with this molecule here? How I'm going to prove that it has a COCH3 group? In chemistry, we have a standard test for this functional group when it's present in a molecule. And this test is called as an iodoform test. And this test can be done in a test tube. All you do is you take your unknown compound into a test tube, add some sodium hydroxide solution to that, and then add some iodine. And then just warm your test tube. And once you warm your test tube, you will form a yellow precipitate. If a yellow precipitate is formed by heating your starting compound, unknown ketone compound, with iodine in the presence of sodium hydroxide, it will confirm that you have a COCH3 group. What happens in this reaction is when you carry out this reaction, you replace all the 3 hydrogens that are present on COCH3 to Ci3. You replace all the hydrogens with iodine. And this Ci3 compound in the presence of base can hydrolyze to give you a carboxylic acid type molecule and a compound called iodoform, CHI3. And CHI3 is yellow in color and is typically a yellow precipitate which falls at the bottom of the test tube. So if you heat up your unknown ketone compound with iodine and sodium hydroxide, and you get a yellow precipitate coming at the bottom of the test tube, you can say, yes, this is my test that this compound has a COCH3 group. And the mechanism of this reaction is listed over here at the bottom. So once you form a Ci3 compound, it shows you how you can get this iodoform and the carboxylate compound. So what we learned so far is that, yes, ketones can form enols, and it can happen under acidic conditions, or it can happen under basic conditions. So it can happen under acidic conditions, or it can happen under basic conditions. And we can do alpha substitution reactions. And the alpha substitution can happen alpha to the carbonyl. And if you do it under acidic condition, it happens only once. But if you do it under basic condition, it can happen more than once. And we looked at halogenation, monohalogenation versus replacing all the hydrogen that are present on the carbonyl group. So what other reactions can we do? Another reaction that is possible by using this enol formation is by alkylating the alpha position. So now we are not looking at bromination, but we are looking at alkylation. And alkylation, we mean if we say that, I'm going to alkylate my carbonyl compound, and I have this carbonyl compound, which is a C double bond O compound, and I'm going to say I'm going to alkylate it. What do I mean? By alkylation, I mean that I'm going to put an alkyl group. And if you represent an alkyl group can be represented by simply putting a R group here, which is like an alkyl halide, say, for example, if this R, and R can be a CH3 group. It can be any alkyl group in this reaction. So this reaction can also be used to put alkyl groups at the alpha position in addition to halogenation, which we have learned so far. Okay. And this happens exactly the same way as we saw in the case of bromination. It can be base-catalyzed. You just remove that proton. So there is protons present here on that CH adjacent or CH2 adjacent to the carbonyl. So this proton can be removed by a base, and you're going to generate that carbanion. And the carbanion can be stabilized by resonance. And obviously, the alkyl halide here act as an electrophile. So that means if this is, say, for example, is CH3 iodide or bromide, say this is, if I write an X here, then the CH3 plus here is your electrophile, and then you can introduce the CH3 at that position adjacent to the carbonyl. So that means you can do alkylation in exactly the same way you can do bromination or halogenation with these molecules here. Okay, so let's see some real example of that now. And one of the questions which sort of you could ask is, what kind of base can I use? What kind of base that is used typically in these reactions? So we saw the example of hydroxide when we were trying to do bromination and iodination reactions. But can we do the same with, say, for example, hydroxide? Or do we need a special base when we are doing alkylation reactions? And the base that is used quite commonly in the alkylation reactions of the carbonyl compounds is a base called LDA. And LDA stands for lithium diisopropyl amide. And the structure of LDA is shown here. And this LDA is derived from an amine called diisopropyl amine. So this is the example of a diisopropyl amine. And this group here is called as an isopropyl group. And you got an isopropyl group on that side as well. So this, and hence the name diisopropyl amine. And the LDA reagent is typically derived by reacting diisopropyl amine with a very strong reagent called butyl lithium, where you can remove that proton here to generate this base called LDA. The reason why LDA is such a useful base in the alkylation reactions is that it itself is a very poor nucleophile. Remember, we're going to try to do reactions of carbonyl compounds. Say if I draw that carbonyl compound again and try to show you why it's important to use a base like an LDA, because the carbonyl group here can also react with the base. The nucleophiles, we learned in the first year that when you just have a carbonyl group, the carbonyl group can react with a nucleophile itself to do addition reaction. The carbonyl group can react itself with a nucleophile to do an addition reaction. So you don't want a small nucleophile which can react with the carbonyl compound. We want a nucleophile which can remove a proton from adjacent CH or CH2 group, but we don't want a base which can attack the carbonyl group itself. So the advantage of using this diisopropyl amide base is that this diisopropyl amine here is a very hindered amine. It got a bulky amine, it got a big flanking group on one side and a big flanking group on the other side. So this NH here cannot attack the carbonyl group because it's sterically very bulky. So the only thing it can do is it can remove the protons that are present adjacent to the carbonyl group. So that's why in the alkylation reactions of the carbonyl compounds, a strong base like LDA is used in these reactions. Because the carbonyl compound pKa is about 17 to 26. So we need a very strong base to be able to remove that proton if you want to do that alkylation reaction. And the advantage of using this LDA is that you don't get any reaction from that amine with that carbonyl group because it is a very bulky nucleophile. It doesn't react with the carbonyl group. It only does reactions at the alpha position. So that's the reason why we use that LDA reaction or LDA base when we are forming the alkylation reactions. So just to prove that, what I'm trying to say here is if you compare the cyclohexanone compound, the ketone compound, its treatment with base to generate an enolate. If we use hydroxide OH minus like the normal base, you will generate an enolate, but you can see this is a reversible reaction. And there is water produced in this reaction. But if you use LDA here, that's our strong base which we have generated. this is not a reversible reaction. You can see that there's a single directional arrow. Single directional arrow means that the reaction is going in one direction to give you that enolate here. So that means you're getting 100% conversion of your ketone to the corresponding enolate. While in the case of hydroxide, this reaction is reversible, and you can see that the pKa of the water is 15.7, while the pKa of isopropyl amine is 35. So this is a very big base, and this is comparatively a lesser weaker base. So LDA is really important in this reaction to drive this reaction forward. And this reaction happens very, very quickly, and you get 100% yield in the formation of your enolate. So if you want to do a reaction, alkylation reaction, the preferred base is an LDA, but it has implications as well. And we'll come back to that implication, which we call kinetics versus thermodynamics. And we'll come back to that a bit later. So basically, if you got a carbonyl compound now, and you treat it with an LDA, with a base, the strong base, and you have THF as a solvent. So THF is a neutral ether solvent. You're going to remove that proton in 100% manner. And once that proton is removed, you got the carbon ion. Carbon ion is going to get stabilized by resonance to give you enolate. And this enolate here then can attack an alkyl halide. This can be an iodide, this can be a bromide. Attack that, Br minus is gone, and you're going to get an alkylation reaction very, very readily. And this reaction can be performed with ketones, with esters, with any carbonyl compound, and you can put a group alpha to that carbonyl group. So you can do that alpha substitution, alpha alkylation reaction using that base and alkyl halide. It can be any alkyl halide. It doesn't have to be a CH3, CH2Br. I mentioned to you already, this can be CH3Br or CH3 iodide. It can even be a benzyl. It can be a phenyl, CH2Br. Any alkyl halide can undergo this reaction to put a substitution alpha to the carbonyl group. Very easy reaction. Okay, now it's time for you to think and for me to be quiet. I got a question for you here. The question is that if I have that compound there shown on the left-hand side, that this is the ketone compound I have here. And the question I'm asking is that if I take this ketone and treat it with LDA, and the structure of LDA is here. So this is a negative with a lithium as a counter ion, which is going to be the positive bit. So that's the your LDA. And the question is, which enolate will be the major product under these conditions? So there are conditions listed here, and we got 4 possible products, A, B, C, and D. And the question I'm asking is, which of these is going to be the major product? So I want you to think about it a little bit, and I'll come to the answer in a minute. But I want you to think, what is the possibility here? We are treating it with the base LDA at minus 78 degrees, and we are asking you which one will be the major product under these conditions. So I'm going to give you a few minutes. I'm going to move to the next slide and come back to this after that. But I want you to think. You can rule out, I can give you a hint, you can rule out 2 structures straight away. Because there is a base, which is LDA. And when you treat that with the base, 2 of these structures can be ruled out straight away. and there are 2 left. And out of the 2, one can form much more readily than the other. All right, let's come back to that in a minute. Let's just go to the next slide. I think I might have another question on the next slide. The other question here is that, which is the major product of the following reaction? You got a ketone here. And what I'm saying is that we treat this ketone now with our LDA, our favorite base. And then we treat it with a methyl iodide. And the question we're asking is that out of this A, B, C, D, 4 products possible, which will be the product of this reaction? This one is an easy one. In the class, when we have a face-to-face, we always ask a show of hands to say who thinks is A or B or C or D. But obviously we can't do that now here. But I want people to think and then compare the answer when I give the answer to see whether they were right or wrong. Okay, let's start here. Let's try to give you some idea what could be the product. What will be the first step? I mean, the first step is to think about is, if you treat this compound with a strong base, what's going to happen? You're going to remove a proton, right? And you're going to see where that protons are. So there's a proton over here. So you got a hydrogen over here. And then you got a hydrogen over here. I can draw it. And then there's a hydrogen over here. So there are 3 hydrogens present. This is a CH3 group, right? While on this carbon here, there is no hydrogen. There is no hydrogen present on this carbon. So it's just a carbon CH3, carbon CH3, carbon CH3. So that means whatever is going to happen on the right-hand side. Nothing is going to happen on the left-hand side because there's no hydrogen present alpha on the left-hand side. So if I remove one of these protons from this position, what I'm going to generate? I'm going to generate a C double bond O, and for a simplicity, I'm just going to call that CH2 instead of drawing the 4 or 3 hydrogens again. CH2 minus. So we're removing one of the protons to generate that, right? And then this group, I'm just going to call that group an R group. So that group is R group. So this is the first thing that's going to happen. You can remove one of those protons to form your carbanion. And obviously this can resonance stabilize. So I can write the enolate structure based on that. So I can just say this can be double bond CH2, CH2. Excuse my writing, it's just the pen is a bit hard to use with that pad. O minus. So this is your resonance stabilized enolate you're going to get if you remove that proton and get that structure, right? And I mentioned to you already that alkyl halide is your electrophile. It loves electron. And oops, sorry. I gone to the last slide for some reason. So you have CH3 and then you have an iodide here. Okay. And this is polarized because, you know, iodide is negative, slightly negative, and this is slightly positive because of the electronegativity difference between carbon and iodide. So what can happen is that this can come across over here. And this can attack your CH3 over here. And then iodide is basically going to go away. So this is going to result in the formation of R, C double bond O, C double bond O. And then you're going to have your CH2 present here. And you're going to get a CH3 attached to that carbon over there. So this is going to be the product mechanistically for this reaction. And if you compare this A, B, C, and D, you can see that out of the A, B, and C, and D, only A is the one which fits that answer. And this one here has got 2 carbons attached to the CH3. This one has got a weird group attached here, and this one have also 2 big groups attached there, which are not possible. So the answer for that question was that the product you're gonna get from this reaction is compound A. Okay, so this is a good exercise to go through to see what product you will get. Okay, if I just go back to the last question now and try to think about that little bit, because there's a bit more involved in this question than the last question we did. I told you already that you can rule out 2 of the products from this already quite easily. The reason is that if you're using a base like lithium diisopropylamide, you can't form an OH because there's no source of hydrogen or H plus present in the starting base. So you can rule this out straight away because they can't form. All we are doing is treating it with the base. And if you're treating it with the base, there's no source of H plus to form that OH group, right? It can only form the O minus compound because you got lithium present. So as the counter ion, so what's going to happen is you're going to get lithium here as a positive, balancing that charge. So there are only 2 possibilities here in this answer. So then the question becomes, is it going to be B or D? So even before we get there, you might ask why they're possible products. So one is I can draw the hydrogens there, which make it a little easier for you to see that if the hydrogens are present, in this case, the hydrogens are present on both sides, and those 2 hydrogens are not equivalent. So that's another thing which is complicating this question, is that if it was a simple cyclohexanone that you had identical groups present on both sides. So if it was this compound here, then you have hydrogen here and hydrogen here. Hydrogen here. So that's like a symmetrical molecule, right? There's total symmetrical structure. So that means the reaction on the left-hand side is going to be same as the right-hand side. But here, this group is not symmetrical. You have a CH2 group on this side and a CH on this side. So that means these 2 are different. These 2, removal of this proton will give you a different product, and removal of this proton here will give you a different product. So there are 2 possibilities in this reaction. That's why you got 2 enols here. There's 1 enol on that side and 1 enol on that side. If you remove the proton on the right-hand side here, you will generate the intermediate, which is going to be the intermediate which has a minus charge here. That's your carbon ion. And then you have your group, which is attached here. And then you also have a hydrogen still here and a hydrogen still here. And and you have a double bond oxygen present in it. So what I'm doing is removing the proton on the right-hand side to give you the carbon ion. And this can resonance stabilize by moving the pair of electrons over here, and this electron going onto the oxygen, and that gives you that structure over here. So that one will give you that one. So if you remove this proton on the right-hand side, you will generate this as your intermediate enolate. But if you remove the proton on this side over here, which I'm going to draw at the bottom here, so basically if I remove that proton, you're going to generate a minus on this side, and you're going to have a carbonyl over here, and then the other side is not affected at all. You just have the bulky group, and you got hydrogen over here. So this is the first anion which will form if you do the reaction on the left hand side, and that will go back over onto the oxygen to give you this as the enolate that will happen. So because the molecule is not symmetrical, there are two different types of CHs present adjacent to the carbonyl. So there are two products possible. Either you get enolate like this, or you get enolate like this. So the question then arises is that which of these enolates will be the major product? So we have worked out that there are two possibilities, there's B and C. And the question is, will B be formed as the major product, or will C be the major product in this reaction? Okay, and that is to do with what we call a kinetic versus a thermodynamic control. And I got one slide on that to show you in a minute. But what I can tell you now is that the LDA reaction is very, very fast, and LDA is a very bulky base. So it's going to remove the proton which is least hindered first. So it's going to attack or going to take away that proton which is easily accessible, because you got a bulky group. You can imagine that a giant group coming to take that proton versus that proton. So I'm going to draw that LDA as a giant group like that. So it's like a big bulky group trying to take away that proton. And when it's going to try to take away that proton, it's going to bump into this isopropyl group that is present. There's a big group present here, and it's trying to take away that proton, and that's going to be harder. But if this bulky group here comes on this side and tries to remove that proton over here, it is easier for it to do because there is no bulk present in the way. So that means the product which you're going to get in this reaction when you're using this LDA is going to be answer C, because that proton is easy to remove compared to removing that proton at the top, because there is a bulky group present next to it. So this product is what we call a kinetic product. So this product is called as a kinetic product. That means it's formed very, very quickly, very, very fast, because there is a very reactive base and a proton that is available which is not hindered. So we call that a kinetic product. But that may not be the most stable product. It is the product which is formed quite easily because that hydrogen is sitting there and you can remove it easily with a strong base, but it may not be the more stable product. That's why we call it as a kinetic product. And this is the product that is going to form. While the other hand, this compound here, compound B, which is the alternative product, is what we call a thermodynamic product. Thermodynamic product is when the product is more stable. When you got a double bond, if the double bond is highly substituted, that double bond is always more stable than the double bond which is less substituted. So if you compare this double bond here with the double bond that is present in B, this double bond has got 4 substituent on it. So this carbon has a substituent, 2 substituent, this carbon also has 2 substituents. So it's more substituted double bond. While this one is less substituted because you got a hydrogen still present at that position. So that's why this product is a kinetic product. It might be less stable, but it is formed quicker. So that's the answer. So since I introduced you to the kinetic versus the thermodynamic concept, I'm going to show you the last slide here for today and show you what do we mean by the thermodynamic versus the kinetic enolate. And this is again the same example or similar example where you have an unsymmetrical ketone. You have a CH2 on one side, you have a hydrogen on one side. So this is your CH2 and a hydrogen here on this side. And on the other side, you have a hydrogen, only one hydrogen here, and the other one is a CH3. Okay, so this carbon is different from the carbon on the left. So left and right carbons are different. So you can either remove this proton here, or you can remove this proton here. And if you use LDA, a strong base, strong hindered base, you will remove this proton like we saw in the last exercise, and you will get a kinetic product, which is easily removable, but may not be the more stable product because this is less hindered. It got a hydrogen here. So that means that double bond is less hindered. On the other hand, this double bond is more hindered, which is the thermodynamic product. So this is formed faster because the hindered strong base will remove the less hindered proton. The proton which is least hindered is removed, while on the other side, the proton is hindered. And if you use a weaker base, or if you leave this enolate lying around, if you let it sit for a while, it will slowly convert into the more stable product, because thermodynamically that is more stable product, and double bond is more highly substituted in this case. And also, if you use a weaker base rather than using a stronger base, the weaker base will take long time to do the deprotonation. And if it takes long time, then the thermodynamic product will predominate in these reactions. Okay, I think I'm gonna stop here and then gonna let you ask me few questions if you like. And if you want, I can finish off. No, I can just leave it here at this slide for today, and then stop presenting, and then I can answer questions if anybody has any questions. So let's just do that. And I just escape out of this. I'll stop sharing probably, and stop share. All right. Okay. So I think I've spoken for quite some time now, and I let you have a little break and then ask questions if you like on what we have covered so far.
Okay. Thank you, Prof. Naresh Kumar. It was really really interesting lecture, and we already have questions from students. So I will just read it for you.
Yeah.
So this is from Andre Safri Maulana.
Yep.
And he asked, like, after I saw the material given from the reaction, maybe this is a general question, but I want to ask how to easily memorize the type of reaction that occur in carbonyl compound, and what should be outlined so that in the future I can easily identify reaction for the carbonyl compound and other compounds.
Okay.
So that's the questions.
Yeah. So I think to understand the carbonyl, you don't have to memorize anything. That's the beauty about mechanistic chemistry and the organic chemistry, is that if you think logically, you can answer any question. Maybe I'll just try to share my screen again and try to scribble something down so that it'll make it easier for you to understand what I'm trying to say. Say if I just share for a few more minutes, what I'll do is I'll just find a blank space, maybe here at the bottom. Say, let's just go back here. Sorry, I just get my pen. Sorry, I just share it again so that I can tell you how to answer the questions when you get questions regarding carbonyl compounds. So I just need to get my pen back so I can. All right, I'll just use this blank space at the bottom here, and I just get my pen. So if you are given a carbonyl compound, you don't have to remember, or you don't have to memorize anything. For a simple carbonyl compound, all you need to remember is that this oxygen is going to be slightly negative, and this carbon is going to be slightly positive. So that means if there is any reaction of a nucleophile, and the nucleophile can be amine, like I said in my slides in the very beginning, if you have an amine, or if you have a alcohol even, or you have any reagent like a Grignard reagent, which is basically an R minus, all you need to remember is that the nucleophiles, this pair of electrons here, or this pair of electrons here, or this pair of electrons here, they will always attack that. They will add to the carbonyl, and this will go over there. And the net result will be that you will get an alcohol here at the top, and you will get the nucleophile added onto your carbons. That's one reaction of the carbonyl compound you need to remember. That's one reaction. That's common to many reagents which add across the carbon-carbon double bond. And what we learned today is, if I just use a razor and try to show you the same thing, what we learned today is that today what we learned is that if you have a proton, which is, if you have a carbon with a proton adjacent to the carbonyl group, say for example, I just take that nucleophile away and I turn that back here like that. So if you have a CH present adjacent to that carbonyl group, it doesn't matter whether this CH is CH2 or CH3 or whatever it is, that you can add an electrophile onto that carbon. So you can add an electrophile, and the electrophile can be a bromine, can be a chlorine, can be a alkyl halide, anything that is possible for that. Okay, so what we are saying is basically in that scenario, your carbon here is negative, and that negative can react with any electrophile which is positive to give you that product in that reaction. So that's the second reaction you need to think about carbonyl compounds. If you can just remember these two general reactions, then you don't have to memorize anything. You just write the carbonyl compound and then you do your reaction and you will have your product. I hope that answers your question.
I think that's really answered the question. I quite agree with your statement. Do we have any question from student again? You also can raise hand if you wish, or just write your question in the chat. Otherwise, I have a question myself.
Yep.
Is it okay? Yeah, because I know that when we have a base,
yep,
base can be also nucleophile, right?
Yes.
Yes, and then you said that therefore we need a certain base to be able to form the negative charge in the carbon.
Yep.
Yeah. So do you have any example like composition, the product when we have a small base that also able to attack the carbon positive in the carbonyl?
Yeah. Okay.
Like what is the percentage of the product? I mean.
Yeah. And again, I'll share a screen and try to explain it by writing a little scheme or just showing how we can. If I can go back to just rubber and just rub this off. So the question here was that if we have a smaller base, can it attack the carbonyl group itself, right?
Mm-hmm.
Say if this is the carbonyl group, and then say instead of LDA, I think the LDA was used to make sure that the reaction goes to completion.
Mm-hmm.
But if you use, for example, a hydroxide as a base, OH minus, or an alkoxide as a base, which is RO minus, which is also a base. Say if you have OH minus, and the OH minus, if it attacks that carbonyl here in the same manner, you can again move the pair of electrons over here. So what you can get is basically you will get O minus, and you have your carbon, and you have OH here, right? This is what you will get. But this reaction is going to be very reversible. So this can come back, and then this can kick out the OH minus, to go back to the original ketone. So with a small base, even though some of the base may attack the carbonyl, but this type of compound here is like a diol, and this compound is going to equilibrium-wise go back to the ketone very quickly. So the advantage of using, say, LDA versus other bases is that LDA makes the reaction goes to completion. Like now we are talking about the carbon, which is over here, and a proton over here, and a proton over here. Say if there's a CH3 here, if we use LDA, you will remove this proton in 100% yield. So the proton will be removed 100% quantitative. You will remove one of the protons. If I use hydroxide or alkoxide as a base, this proton might be removed only in small proportion. And if it's removed in small proportion, and the removal of proton with a weaker base is going to be a reversible reaction. So if I use hydroxide to remove that proton, I still will generate the carbon with a negative charge, but it will be to a less extent, and it'll be like a reversible reaction. It'll keep on going back and forth, back and forth, back and forth. And the product of the reaction will take longer to form. And also that will mean the product that will form will be the thermodynamic product. You won't get any of the kinetic product if you use a weaker base. So that's the advantage of using a stronger base and a bulky base. But if the base attacks the carbonyl group, then it's a reversible reaction, and the equilibrium is lying towards the ketone compound, not towards the diol compound. So that's the reason why we need a stronger base in the alkylation reaction. The nucleophilic base can attack the carbonyl, and it will only survive if there's some sort of stability. Otherwise, it'll just go back to the carbonyl compound.
So basically, at the end, we have more reactant than product then.
Yes, exactly.
Okay.
Exactly.
Okay.
Like alcohol can also react with the carbonyl group, right? If you take methanol or ethanol, you can react the carbonyl group with a methanol or ethanol. But the reaction is quite reversible. Unless there is some sort of stability built into it, it will go back to the starting compound. And the reaction of excess ethanol, for example, with a carbonyl compound, you can form a ketel or an acetal compound, which can be isolated. But if you have no acid catalyst present, and you just take your ketone compound and you heat it with alcohol, you will just get this equilibrium where the major product will be the ketone still. Yeah.
Okay, thank you. That's very clear. Yes, we still have 2 questions, so I will read it for you. So the first one, oh my God, this is quite long. Okay, from Axel William Fried. And he asked about the first question, a few questions about the carbonyl compound. And he said, like, we knew that the carbonyl compound able to do tautomerism, which the keto can be changed into enol. Also, due to the intermolecular interaction, makes the enol more major than the keto. So the point of my question is all the carbonyl compound that able to do tautomerism are always major in enol state?
Okay, let me answer that first. So there has to be some sort of stabilization for it to be going into the enol form. Like the diketone I showed you earlier, which was a 2,4-diketone I showed you, the hydrogen bonding was the driving force, the intramolecular hydrogen bonding. And the hydrogen bond formed was a 6-membered ring. If you remember that structure, it was a 6-membered ring. 6-membered, 5-membered ring hydrogen bonds are quite favored. They're quite stable. But if you start to form 7-membered or 8-membered hydrogen bond rings, they are less likely. So that means the carbonyls which are present in 2,4 position, they are the one which are going to form the enol readily. But if you have a 2,6 or a 2,7 dicarbonyl compound where the two keto groups are present far away, and you try to form an enol, it's not going to be stabilized by hydrogen bonding because the ring is going to be very large.
Yes. Yeah.
So the carbonyl groups have to be forming a 6 or a 5-membered ring hydrogen bond to be able to form that enol form. Otherwise, the other carbonyl, dicarbonyl compound will just behave like a monocarbonyl compound.
Okay.
Where you can we can form the enol with an acid or a base, but not existing in the enol form by itself.
Yes. And then this is the next question.
Yeah.
So if the compound have like more in the enol state, and then we want to make it in the keto state,
Yeah.
Can we do something about that?
So the question is always to drive the equilibrium from one side to the other.
Mm-hmm.
So like the example we saw in the case of diketone, 76% was enol and 24% was ketone. So if you want to go in the other direction, you want to convert the enol into the keto form, then you start using the ketone somehow. Mm-hmm. It's like an equilibrium. If you start removing or start reacting the ketone, then the equilibrium will shift to the other side. Mm-hmm. And then the reaction will go the other way. So there has to be some sort of driving force. There has to be some sort of reaction which is consuming that product. Mm-hmm. And if it's consuming the ketone, then the whole equilibrium will shift towards the ketone side.
Yes.
Yeah.
So this is about equilibrium then, yeah?
Yes, that's right. That's right.
Okay. And then still the question from the same persons. Do you have any tips to determine the major of the product? Yes.
So I think the thing to look for there is like I was answering the first question is mechanistically which one is going to give you a more favorable product. So you can, by looking at the two possibilities, which is going to be the favorable product, if you think carefully, logically, then that's going to be the major product. So, in organic chemistry, you can sometime or many times or most of the time can predict by drawing arrows that which looks like likely the more favorable product. And actually, when you do the reaction in the lab, you will find that it's the same product is the major product. So like I gave the example of a thermodynamic versus kinetic control.
Mm-hmm.
Yeah. If you do the reaction quickly under using a strong base, hindered base, this is going to be the 100% product. Mm-hmm. But if you use a weaker base and let the reaction sit for a long time, then it's going to be the thermodynamic product. So you can predict and look at the reaction and tell that this is going to be the major product, depending upon the conditions you're using.
Okay.
Yeah.
Oh, I still have the questions.
Right.
Okay. This is Novel from UNPAD.
Yep.
So the question is, sometimes we have asymmetric ketones as a precursor, and it's able to do cross condensation and then generate alcohol with new chiral center.
Yeah.
What the strategy to control the stereoselectivity that arise from this kind of reaction?
Okay, so if you have a carbonyl compound, and it's going to depend upon what is the adjacent group to that carbonyl. If you have a bulky group present adjacent to the carbonyl, then the incoming reagent has to come from one side or the other side to avoid that clash. And that's what can lead to what we call stereoselectivity. That means the reagent can either come from the top or from the bottom, because there's a big bulky group sitting next to the carbonyl group. So the groups that are present adjacent to the carbonyl group can control the stereoselectivity of the reaction, which is going to happen. If the group is present, the reagent is going to avoid that bulk, which is present adjacent to the carbonyl group. If the bulk is present on top and next to the carbonyl group, the reagent will come from the bottom. And if the bulk is present at the bottom, then the reagent will come from the top. And that's where you can get the stereoselectivity in that reaction. Okay, and I think the next question was, if we continue eliminate the alcohol, it can give new double bond Z or E isomer. What strategy to give the stereoselective product? So the selectivity, I think, comes from the hysteric hindrance that is going to form also in your alkene. If you're taking the alcohol to form a double bond, then if there is a lot of steric hindrance, that is also going to determine whether you get E double bond or Z double bond. So there, the steric hindrance determines whether you get the trans product or the cis product. So there is, when you dehydrate the alcohol, you can get a cis product or a trans product, and that is another factor as well, which need to be taken into consideration. But in the thermodynamic products, the substituted alkene is always more stable than the less substituted alkene. So there are two things, I suppose. One is the steric hindrance, and second one is the thermodynamic versus kinetic product.
We have the last questions.
Yeah.
In the base promoted halogenation, why does the product still contain bromine ions, even though both of bromine has been substituted in alpha hydrogen?
Why the product still contains bromine ions, even though both bromines has been substituted in the alpha hydrogen. So I think the hydrogens which are present at the alpha position have been substituted by the Br. Maybe I can take you back to the slide so that you can see if there is any confusion there. I'll just go back. Pen is there, so I just go back to the previous slide where we have the bromination. I think this is the reaction we're talking about, base promoted bromination. So you can see that when you have hydrogens here, bromine in the presence, because bromine is used in excess, and the base is there. So you replace both of these hydrogens with bromine. And if you have 3 hydrogens present adjacent to the carbonyl as CH3, you can replace all these 3 hydrogens with CBr3, with 3 bromo.
Yeah.
So I don't know what the question is, because the hydrogens are replaced with the bromines in that reaction. And same thing happened when we have the iodide, and we replaced all the 3 hydrogens with iodide, and the side product that is formed, once the Ci3 is formed, it can hydrolyze to give the corresponding iodoform compound. So it's the hydrogens that can be replaced with the bromines. In the base promoted halogenation, why does the product still contain bromine ions?
Maybe because in the reaction, one of the reaction, you still have like ion bromine not attached to the carbonyl. I think this is the excess of the excess of the
excess reagent. That's right. Yeah,
because the excess of the reagent. Because you use the excess of the bromine. Yes.
That's right. Yeah.
Okay. So I think we come to the end of the session, because now it's like 6 here, and I think we also have no question anymore. I hope if you still have, maybe you can deliver the question for the next session. Yeah, Prof.
All right. Yeah, I think we can answer in the next session. Yeah, next week.
For the next week. Yeah. Okay. Thank you very much, Professor Naresh, for a really interesting lecture. And on behalf of Department of Chemistry Education of Universitas Pendidikan Indonesia, I really thankful for the really nice talk and also the discussion. And I think I will see you again next week. Yeah.
Next Thursday. The remaining slides. Yeah.
Yeah, for the next session. Thank you very much for all the participants for this afternoon. And then maybe we can close this by saying Alhamdulillah, Alhamdulillahirabbil alamin. Thank you very much, Profesor Naresh, Pak Asep, Ibu Gebi, kemudian saya lihat Bu Ratna, Bu Vidya, for coming to this session. And then see you next week. Thank you, Prof. Naresh.
Thank you.
Yeah.
Bye-bye.
Thank
Okay,
you,
bye.
Prof. Naresh.
Yeah. Thank you also for our student ya.
Yes, thank you buat semuanya. Terima kasih sudah hadir. Kita akan ketemu lagi di